Okay, so welcome everyone. So today it's my pleasure to welcome Shi Jin, who will be talking about dimensional lifting for quantum computation of partial differential equations. Yeah, thank you.
Okay, should I start?
Yeah, please go ahead. Yes.
Oh, okay, sure. Hi, everyone. Thank you for taking your time to attend my talk, and thank the Median for arranging this talk for me. It's a really a great pleasure to be here to share with you my recent work. It's pretty much what I've been mostly doing research-wise in the last 2 years. So it's a new area for me. So it's about quantum computation for partial differential equations. So this is basically I try to cover, or it depends on how fast I can go. So first, I want to give you a very simple introduction about quantum computing. And bear me, I mean, if you're already expert in this direction, just in case, because it's a new area for many mathematicians. Then I will talk about the linear PDEs, essentially like to nonlinear. Then time-dependent PDEs and ODEs with time-dependent coefficients, namely non-autonomous systems. And then if I have time, we'll talk about the random coefficients. All right, so this is basically the difference between a classical computer and a quantum computer. I mean, a classical computer, as you all know, we represent the signals by this binary representation, 0 and 1s. So you do some operations and you output signals also of 0 and 1. While quantum computing is done on so-called quantum state. Right, so that's actually a high dimensional unit vectors in a complex plane. I'll explain later. Then the basic operations is so-called quantum gates, which are actually unitary operators and unitary matrices. All right. So because the unitary operators preserve L2 norm, so if you start with quantum state, which is a unit vector in complex plane, you end up after quantum gates, you end up at quantum states, right? So it's a unit vector to unit vector, and you multiply by unit matrices. Basically, that's essentially what quantum computer does. Okay, just do this. Start with quantum state unit vector, you multiply by unit matrices, you end up at another unit vectors. Of course, this quantum state is not really the classical data. Like if you solve PDEs, you want, for example, fluid equations, you want to get velocity, density, temperature, and so on. They have to take so-called measurement. And that's usually very expensive. Okay, this is the bottleneck for doing quantum computation. How to get classical data from quantum state. And these are some very basic ingredient in quantum computing. So we start with these classical bits. All right. So this is the two-dimensional basis functions. This is Dirac notation. Ket. The right array means I will call it the ket. So the 0 is basically 0, 1, this two-dimensional vector, but one ket is the 0, 1, all right? So this is basically the basis for a two-dimensional vector space. A quantum bit or qubit is a linear combination of these two basis vectors, but in complex plane, okay? So here A and B are complex numbers, and you normalize it, all right? So it's unit vectors. I mean, it's like it's a point, a vector in this unit sphere, while the classical bit is just two vectors, 2 points on the sphere, while the quantum bits represent all possible points on this sphere. All right, so we're going to compute simultaneously all the informations on this sphere, essentially. And so that's only one qubit. All right, if you have a high dimensional vectors, I mean, if you have m qubits, they can represent information in the dimension of 2 to the power d. All right. So if you have work on d-dimensional Hilbert space in complex Hilbert space, all you need is n quantum bits, qubits, which n is just log base 2 of d. So that's why if you design algorithm carefully, you can get so-called exponential speed up. It's really because for dimension 2 to the power n dimensional space, you just need n qubits. All right. But that's when you use the so-called qubits. You can also, there's also direction you call continuous variable. Instead of using all these vectors, here all these qubits are vectors, you can use continuous variable, okay? X is continuous variable. And then, of course, a Q mode representation is this continuous variable representation for one Q mode. If you have D Q mode, then you can represent the vectors in D-dimensional space. And as I said, quantum operation is basically you multiply by unitary matrices, okay? And you do not, to design quantum circuits, you only need 4 basic unitary matrices. They are all given here. There's 3 here, Hadamard, phase, and pi08. It's just 2 by 2 unitary matrices. You also need this 4 by 4 matrix called a control NOT gate. It's a 4 by 4 matrix with the first 2 by 2 is submatrix is just identity matrix. Then the last 2 rows is simply switch the third and fourth element. So this is a very important theorem called the Solavy-Kitav theorem, which says the following. It says, given any unitary matrix, okay, if you require the accuracy to be epsilon, you can just find, they can approximate it by these 4 basic unit vectors to arbitrary position epsilon. So these 4 unitary matrices are so-called universal unit, the gates, quantum gates. Okay, basically you just use these 4, can approximate arbitrary unit matrix to any position. Okay, so basically just need these 4. So for example, suppose we have in 4 dimension, all right? So then the 4 basic basis functions are just you do tensor product of 0 and 1, all right? So then you have these 4 basis vectors. And if you, for example, you apply control NOT gate to these 4 vectors, then the first 2 basis vectors will remain unchanged because you have this 2 by 2 submatrix in this control NOT gate. And the third and fourth vector, you just switch them, right? So that's just one quantum operation, a quantum gate operation. And we often represent a quantum algorithm by these so-called circuits, all right? So we just draw a diagram. For example, if you start with quantum gate, quantum state per psi, you multiply by unitary matrix U, you end up at U times per psi, all right? It's just a vector multiplied by a matrix. So these are some examples where X and Z are just Pauli matrices. And the control NOT gate is a 4 by 4 matrix, so you act on 2 qubits, all right? So you have 2 qubits. So if the first qubit qubit A is 0 and it remain unchanged, if it's 1, you add to the second bit, but the summation here is mode 2 summation. So if it's 2 equals 0, okay. And the lower right is a famous algorithm called quantum phase estimation. This is the quantum analog of this power method to find the largest eigenvectors or eigenvalues of a given matrix. All right. Remember this power method. Basically, you start with any initial guess, you multiply by the same matrix many times. Eventually, the largest eigenvector will remain. Okay, will dominate and remain. So that this algorithm does essentially the same thing on the quantum computer. So the first, so suppose you work on m bit on qubit. So first m minus 1 qubits you multiply by this Hadamard gate. The last qubit you multiply by this matrix U many times. Okay, so it's like power method. An important algorithm is the quantum fast Fourier transform. We know, I mean, the class for discrete Fourier transform is all n square complexity when you have you want to use m piece of data to do discrete Fourier transform. So classical FFT reduce that to n log n. Okay. However, if you use quantum FFT, then you just need the complexity is just log. You take a log on the whole thing. Okay, you take log n square. So that's why you get so-called exponential speed up. Okay, from whatever classical complexity you take a log, you get exponential speed up. And of course, from quantum state to classical data, you have to take a measurement. Essentially, the measurement means that you have what do we just to talk about quantum algorithm is basically subroutine. From you start with quantum state, you operate by quantum gates, and you end up at quantum state. And then you have to measure, if you want classical data, you have to measure the probability of certain outcome in the computational basis, right? It's like this A and B, and A squared is probability that the 0 appears, while B squared is probability that this qubit 1 appears. So you have to measure the probability. And this is like Monte Carlo. You have to sample many times, you take average. So the cost of measurement usually is very much larger than the quantum subroutines. It's like this Schrodinger cats, right? With certain probability is dead or alive. So that's a quantum state. And to see whether it's dead or alive, you have to open the box. So that's a measurement. And you have to usually do this many times because it's probability. The outcome is probability. Quantum computation was expected to be revolutionary for the whole world, and has already had many important development in quantum communications, information science. But what we are interested is to use quantum computer to solve scientific and engineering problems, right? Scientific computing, quantum scientific computing. In scientific computing, of course, the most elementary problem is to solve a linear algebra system. Okay. So here, the first milestone in so-called quantum linear algebra solver is this algorithm developed by Haram, Hastim, and Lloyd. It's called a HHL algorithm. And there's some later improvement more recently. So for example, if you want to solve this linear algebra from mx equals y, where m is a matrix of 2 to the power m by 2 to the power m matrix, then the classical algorithm, for example, Gaussian elimination, is basically the matrix size cubed. Okay, so that's the class complexity. While the quantum algorithm, of course, you have to start with the right-hand side, it should be quantum state. And then you want to find the quantum state of x. So essentially you solve x cat equals m inverse y cat, all right? And this quantum algorithm has a complexity, it's a log of 2 to the power m. So you really get exponential speed up, all right? And the complexity of this algorithm is like this. So here's O tilde. Tilde means I ignore the logarithmic factor, right? So it depends on the maximum norm of a matrix M. But here the maximum norm is just the largest entry of the matrix in absolute value, okay? And kappa is the condition number. And S is so-called sparsity, which is the largest eigenvalue. And the condition number is the largest eigenvalue over the minimum eigenvalue. And S the sparsity, which is the number of non-zero entries in the rows or columns of M. Okay, so it works very well if you have a sparse matrix, and if the condition number is low. What we are interested is to use quantum computer to solve ODEs and PDEs, and also with probably many initial data. And very often, if you do a stochastic PDE, for example, use Monte Carlo, you have to take a lot of samples. You have to solve the equation many times. So these are the kind of problems we are very interested in solving, and it's a major part of the scientific computing. Well, actually, the quantum computer is designed using quantum mechanics principle, all right? So essentially, it only knows how to solve one type of PDEs, which is the Schrodinger equation. So that's the fundamental equation in quantum mechanics, all right? So here's the Schrodinger equation where U is just the complex valued wave function, all right? I is just the square root -1, where H is the quantum Hamiltonian, which has two parts. The first part minus Laplacian is the kinetic energy. And then you have this potential energy V of x, all right? So that's the Hamiltonian. And Hamiltonian actually, this is the Hermitian matrix, okay? It's Hermitian matrix. And so the analytic solution to this Schrodinger equation is, if you start with initial data U0, okay, it's quantum state of U0, evolutions of the operator is e to the minus I ht. And because H is a Hermitian, e to the minus I ht is a unitary, okay? So you multiply initial data by this unitary operator, then you end up at the U of t, which is also quantum state because the unitary operator preserves L2 norm, right? So start with unit vector, you end up at a unit vector because H is Hermitian. So why quantum computer simulation is basically, it's a quantum mechanics experiment. So you have this quantum channel here, which corresponding to this given Hamiltonian. Then, for example, you inject a beam of photons or laser. Okay, and that's the initial data. You collect the output at the other side. So that's a quantum simulation. It's just quantum mechanics experiment. And notice that the Schrodinger equation is conservative or preserved L2 norm, all right, because the evolution operator is unitary, and it's time reversible. It's a Hamiltonian system. Okay, you can go backwards in time. So that's essentially what quantum computer does. Okay, you can only do this, or can only simulate the Schrodinger equation. And now, how about the general other differential equations? For example, here we have a parabolic equation, right? Hit equation. So L is just Laplacian plus maybe some forcing term, okay? And of course, here, we can multiply both sides by I, and then this A is IL. Then clearly A is not Hermitian. In general, A is not Hermitian, okay? For Hit equation, A is not Hermitian. In fact, I mean, parabolic equation is dissipative and time irreversible. So quantum computer cannot simulate this equation because it's not evolution operator is not unitary. All right, actually, it's the L2 norm decays for this equation. So it cannot simulate the equation like this. So so basically what today I'm going to cover the following topic. So, well, the process of solving Schrodinger equation is called a quantum simulation. All right. So essentially, the quantum computer can only do quantum simulation. It's like you have an infant, you just have a newborn baby. The baby can only drink mother's milk or formulas, right? If you give them fish and chips, and the infant cannot eat it, okay, cannot digest. All right, so now we ask the following question. Number one, can you do quantum simulation for other PDEs and ODEs? Okay, they are not Schrodinger. So here we are just classify two types of equations, either Schrodinger or the other PDEs, all right? Schrodinger or non-Schrodinger. Can you do quantum simulation on non-Schrodinger equations? Okay. And second question, well, quantum mechanics is essentially linear. Okay, Schrodinger equation is a linear equation. Then how about nonlinear equations, nonlinear ODEs and PDEs? Okay, can you do quantum simulation for nonlinear differential equations? And then how about time-dependent Hamiltonian? Very often you have ODE PDEs where the coefficient depend on time, so-called non-autonomous dynamic system, right? And then more broad, I mean, the coefficients may be random, stochastic, random coefficients, and so on. So these are problems we try to solve. Well, the first question about non-Schrodinger PDE, and we believe we find a very nice generic way to handle it in a systematic way. Okay, what we call this Schrodingerizing. Essentially, we find a way to Schrodingerize all non-Schrodinger equations. Okay. So we we use this word. I mean, we thought this word is probably people have already used it. Actually, if you Google, you find nobody used this terminology, which is I'm a little bit surprised. So we call this method Schrodingerization. All right. So John worked with Nana Liu, who is excellent young quantum physicist, and she was trained in UK actually. She got her PhD from Oxford. Yu is our postdoc. So let me use a simple example of Hit equation, all right? DODT, I mean, it's equation everybody knows how to solve. And here, of course, assume it's a very high dimensional, D-dimensional problem. So we just introduced this very simple transformation we call the warped phase transformation. So the U, of course, depends on time and space, T and X. We multiply it by e to the minus P. Now we have this W function, which depends on one dimension or higher. All right, so we add one extra dimension by this variable P, where P is positive, okay? That is a very simple calculus. Of course, if you multiply this Hit equation by e to the minus P, W solve exactly the same Hit equation, right? Now notice that dW dP is minus W, okay? Because derivative of e to the minus P is minus e to the minus P. So dW dP is minus W, then we change the W behind the Laplacian by minus dW dP. Okay. And then we get the third order PDE for W, and you have this one derivative in P and two derivative in X. Okay. Suppose you can solve this equation for p positive, and to get back to u, you just integrate over p from 0 to infinity, right? Because integration of e to the minus p from 0 to infinity is 1. Or you even don't have to take integration. Notice that if you e to the p of times w equals u, so u does not depend on p, which means e to the p times w does not depend on p. So essentially you can pick any p positive. You just multiply by w by e to the p, you get back to u for any p, right? All right, now the first question is that we have a third order PDEs. This is a good PDE. You want to make sure it's a good PDE. And to see that, we just take a Fourier transform on x, okay? We take Fourier transform on x. Then of course you have two derivatives in x. Okay, if you take Fourier transform, we get a minus this Fourier mode cosine squared. Now you get this doublet hat in the Fourier space. It's actually a just convection equation. It's a linear convection equation, or in P, where the speed of the propagation is always negative. It's a minus cosine squared, right? So you have convection equation where that it's a wave which moves from the right to the left in the P space. Remember, we're solving the half space problem for P positive. P is from 0 to infinity. So the wave is moving from the right to the left. So you do not need the boundary condition at P equals 0. Okay. But you need the boundary condition at P equals infinity. But notice here we can truncate because solution decay exponentially in P. Just stop at some finite P large enough so that the e to the minus P is almost 0. They just give a 0 boundary condition on this right-hand side. Okay. Then we have a well-posed initial boundary value problem. Okay, well, I mean this problem is well-posed. You can solve it. It's a good equation, right? Okay, now what's the relation between this third order PDE and the Schrodinger equation? Now we just extend this P to the entire domain from minus infinity to infinity by doing even extension. Okay, I even extend this initial data of W. I put absolute value of P. Okay, it's even function, the initial data in P. Now look at this equation, the new system with this new in the entire space. Now I take Fourier transform on P. Okay. And you take Fourier transform because it's the first derivative in P, you get this I times this Fourier mode eta, right? Now look at this equation on W tilde. That's exactly the Schrodinger equation. All right. So this is the equation that the quantum computer can simulate. You can do quantum simulation on this W tilde equation. Okay. And of course, to get back to W, you have to take the inverse Fourier transform. But remember, we have this quantum FFT. You can use that. So everything can be conducted by quantum simulation, quantum algorithm. Okay. All right. Now, when we first realized this, people kind of find this intriguing because all of a sudden we start with a disruptive system, Schrodinger equation. It's time irreversible. Now we get the system which is time reversible and this Hamiltonian system. How can that possible? How is that possible? Well, here I have a very graphic representation of why this is possible. So here I just plot W versus P. Okay, but clearly the W equation is conserved. Both L1, L2 normal conserved, right? This W equation, right? Because it's divergence form. It's linear, and so. But what is U? U is the integration of W over P from 0 to infinity. So U is the area of the right-hand side of this curve, W curve. This area of this shadowed zone. So the W is a wave that moves from right to the left. Okay, so you see the U actually is decaying, right? The energy of U is decaying because the wave is moving from right to left. So the area will shrink, but W is conserved. So in the lower dimension, you lose the energy is dissipated, but the lost energy is preserved in the higher dimension. Okay, and you only need to add one dimension to do that. Before, of course, people think, oh, you have to go to quantum mechanics, use embodied Schrodinger equation, you have H bar, all these things. You do not need that. All you need is just go to one dimension higher, take a Fourier transform, you get a Schrodinger equation. And you may think, well, heat equation may be very special. You have Laplacian, whatever. Actually, we can do this for general linear dynamic system, both ODEs and PDEs. So here is general dynamic system, all right? Well, A can be just linear operator or differential operator, doesn't matter. Okay, so you include PDE. Or you discrete the PDE becomes ODE anyway. So it cannot, every linear dynamic system, PDE can always be written in this form. But of course, in general, what this diagram means complex conjugate does not equal to A, okay? In general. For Schrodinger equation, A dagger is A, but for general PDE, it's not. So what you need to do is just decompose A into a Hermitian plus anti-Hermitian matrix. But the Hermitian part H1 is A plus A dagger over 2. While H2 is A minus A dagger over 2I. All right. So clearly both H1 and H2 are Hermitian. Okay, so A can be written as one Hermitian plus I times another Hermitian. Now this IH2 part is already the part we like because it's I times Hermitian matrix. So that's, if you take E to the IH2, that's unitary, right? But H1 is not. This is more like H1 is like heat equation, where H2 is like a Schrodinger equation. Okay. But now for the H1 part, we go to high dimension. We multiply the U by e to the minus P. And then of course, H1 part, you get this minus dV dP. You will do exact same thing as we did for the heat equation. Well, H2, we do nothing. Okay, because already the form we like. Now for the H1 part, the P derivative, we take a Fourier transform on P to get the I, because we need this I. Well, you have this Fourier mode, eta, but that's a scalar. A scalar time Hermitian is still Hermitian. Okay. So, of course, I mean, numerically, you probably want to do a discrete Fourier transform. So here, assume that the mu1 to mu_m is just the discrete Fourier modes. Then essentially just have to solve this double hat equation. All right, so d double hat dt is with minus I times H1 tensor with this diagonal matrix, with diagonal entries are just discrete Fourier modes. Well, H2 you tensor with identity because we do nothing about H2. Now the right-hand side of double tutor equation is I times a Hermitian matrix. So you can design a quantum algorithm just based on this double tutor equation. All right, and this is very generic. Remember, this A is general linear operator. Any linear operator or differential operator. And H1, I think it's very difficult to design algorithm which is simpler than this because H1 and H2 only involves A and A dagger, a linear combination of A and A dagger. All right, but I mean, you need to solve A dagger anyway. So I can imagine one can find a quantum algorithm which is similar than this because that's essentially we just use A and A dagger. Okay. All right, now, of course, because this method is very generic, so we can solve all kind of linear PDEs, you name it, from this one linear Black-Shore to transport equation for Planck and so on, and even Maxwell equations, all right. And you can also use it to, to generate ground state and Gibbs state, because you can solve the evolutionary equation to steady state, okay. And also, we can also do when you solve PDE, you should have boundary value problem or some interface problem. You have wave propagate through some different media. And of course, usually the boundary value operators are not the unitary operators. But we can use the same transformation to even transfer a non-unitary boundary value operator into a unitary one by exact same transformation. Okay. Also for interface condition, for example, you have a wave transmission, reflection through a barrier. You can also, I mean, they can, all these operators can be unitarized. And you can also do a linear algebra problem, discrete dynamic system, right? So here I give example, for example, for linear algebra, iterative method, for example, Jacobi iteration is the way to solve a linear algebra system, where the power method is the way to find the eigenvalues, large eigenvalues. And all general linear, discrete linear dimension can be written in this form. So you have yk plus 1 is some linear matrix G, is matrix G times yk plus some inhomogeneous term. So all the iteration method can be written like this. Of course, here we have this inhomogeneous term G, but you can just add one component, say 1, to make this inhomogeneous system a homogeneous one. Okay, so you have this homogeneous system for X. Okay, you just add one component to Y, you make it homogeneous, get rid of this G. And then, well, you subtract this both sides by minus xk, then you can view xk plus 1 minus sk as a time derivative. It's discrete time derivative of dx dt. Then you have this continuous, it's ODE now. We have ODE. And you can Schrodinger this ODE. All right. Then you solve this ODE to steady state, you get the convergent solution to the iteration. So basically, I mean, you can Schrodinger all these linear iterative schemes for linear systems. And actually, with this, actually, I want to talk a little bit about remember our formulation is continuous, it's based on continuous variable. It's from PD to PDE, and this transformation is a continuous variable. We never use this discrete, we do not have use discretizations, right? So it's from PD to PDE. So that allows us to do so-called analog quantum computing. Well, when we talk about quantum computer, we know that usually people know that we have to use qubits. But the reason that nowadays we do not have a quantum computer available for our application is because now all these qubits are very noisy, all right? When you do not have enough qubits, and you just generate garbage. I mean, now, I mean, for later results for IBM, they have like 1,000 qubits. And they're so noisy that the output is just, you cannot trust. Okay, you need lots of qubits, maybe to solve PD, maybe probably need millions. So you probably have to wait a little bit. Okay, I don't know how long. And optimistic people think maybe 10 years. And if you're not very optimistic, maybe, I mean, a few decades. But because our formulation is based on continuous variable, well, after all, PDEs are continuous variable anyway. And this allows us to do what we call analog quantum computer, all right? Which means that we are working with experimental teams. You just do a design experiment based on this quantum Hamiltonian that we found for general PDE. And if that's successful, which means that now we have a quantum device it's called analog. It can be used to solve specific PDEs. It's not a general purpose quantum computer. It's specialized quantum computer, which can be used to solve certain kind of PDEs. So that's what we think will be more near term. And the system based on qubits, as I said, it will probably be long term. But in the next few years, we hope this analog quantum computer is more realistic. Okay. So, well, if you have, I mean, probably most of the audience are too young to remember that even for classical computer, before the 70s is when the digital computer becomes dominant. But before that, I mean, everyone was doing analog computers, all right? I mean, obviously in the US, in everywhere, where people are doing the class. Basically, you have just the computer can only be designed to solve specific problems. And actually, even classical analog computer has a new revived. For example, here, this is MIT News, which says that analog quantum returns because, I mean, now this general purpose classical computer is it's not energy efficient. For example, if you want to do chat GPUs, AI, and you need a lot of GPUs, a lot of energy, a lot of electricity to support it, right? So actually, the classical analog quantum computer has a new becomes quite active. And people are interested to design so-called energy efficient PDOD solvers. I mean, these are the group from Cornell, Columbia, and so on. So this is the direction we are pushing on. So what we can do? So this is what we can do. Give me a PDE, all right, any PDE. We can Schrodingerize it, which means we find this Hamiltonian, unitary Hamiltonian. Then we quantize it, all right? We just change X to this X hat, which is the position operator. Well, we change the derivative, spatial derivative into the minus IP hat, where P is the momentum operator. Then we have a quantum Hamiltonian. We give that quantum Hamiltonian to the physics experiment. If they have quantum device, which basically is almost the same as our quantum Hamiltonian, then that device is essentially analog quantum computer. Okay, so that's what we call a special purpose quantum computer. For example, for Maxwell equation, we found a Schrodingerized Maxwell equation, even with boundary conditions, all right? So this H is quantum Hamiltonian for Maxwell equation is given here. It's a little bit complicated. What is sigma z, sigma a Pauli matrices? All right. So if the experiment can realize this quantum Hamiltonian, then essentially we're going to have a quantum computer for Maxwell equations. So that's what we are working on now. Now we're working with 5 different very top physical experimental team to do this kind of experiment. So this is what we call I call the user's guide for quantum Hamiltonians. So essentially for all these linear PDEs, we find the quantum Schrodinger version, and then we find corresponding quantum Hamiltonian. Now we're seeking experimental team in the world to see whether their experiment can correspond to one of these Hamiltonians. So that's what we try to do. So as I mentioned, we are working closely with 5 experimental team in China. They're all top-notch quantum physicists. And they are very excited doing this because they find new applications for their quantum device. All right. So that's the story about the linear PD and linear system. So now how about nonlinear equations? I don't have to tell you, I mean, there are lots of important applications for nonlinear problem, right? Fluid dynamics, molecular dynamics, these are all nonlinear problems. Difficult with nonlinear problem is that, I mean, not only is nonlinearity or maybe high dimension, and the solution can be very bad. You have singularities like shock waves, blow up, and so on. Okay. Well, the quantum computer is designed based on quantum mechanics principle, and quantum mechanics actually is linear. All right. So people already attempt to see, can we design a nonlinear quantum computer? All right. So this is a paper published in the Physical Review Letter by Seth Lloyd. Remember this HSL algorithm, the first quantum linear algebra solver, and this L is him, okay, Seth Lloyd. So he was trying to have a nonlinear quantum computer solve, for example, Berkeley's equation, nonlinear Berkeley's equation. That's the conclusion of his paper. He said, finally, we would like to note that we believe that quantum mechanics is in all likelihood exactly linear, and that the above conclusions of this paper might be viewed most profitably as further evidence that this is indeed the case. All right. So essentially, he said, well, essentially, quantum mechanics can only solve linear problems. All right. This paper still confirms that. Well, he said, nevertheless, the theoretical implication and practical applications that would result from a discovery to the contrary may warrant further investigation into this matter. So it's really, we need further work to just try to see whether, we can solve a nonlinear problem. Well, with this, then there's only 2 routes to solve a nonlinear problem. Well, first, you just abandon this quantum, the design principle by Richard Feynman, actually. Okay, forget about this quantum computer framework. Don't use quantum mechanics, right? But that seems to be, I don't know. I don't think anybody has an idea. Right? We probably take another Einstein to think of a new way to do this quantum computer. But the second route is that there's no choice. Can you make the problem linear? All right. Of course, we mathematicians know how to make a problem nonlinear. Linear is just do linear approximation. Okay, there are all different ways to do it. You linearize around constant. You linearize around maybe the global equilibrium and so on. So that's what people do before us. Right, the most popular method is so-called Kalman truncation. The way Kalman truncation is the following. So suppose you have a Riccati equation, du dt is minus u squared. You call u squared to be v, then you find the equation of v, which is still nonlinear. Then define the next nonlinear term to be w. You write the equation for w. All right, and you just continue. And if you allow infinite dynamic system, that's linear. But of course, you have to stop to have a finite number of, it's like moment closure, you have to stop somewhere. And the last equation, you just throw away the nonlinear term. That's called a Kalman truncation. But of course, we know if a nonlinear problem, if you throw away nonlinear term, then the validity of the model is questionable. It may be valid only for a short time. Okay, you lose a lot of important nonlinear physics. But what we advocate is that can you find an exact mapping which maps equivalently, all right, equivalently, without any approximation, you map a nonlinear problem to linear one. So that's the approach we have been trying. Of course, you cannot do this for all nonlinear equations. But we did find two types of equations where we can do this. All right. One is the Ham-Jacobi equation, and that's given here. ds dt equals Hamiltonian, and this Hamiltonian depends on gradient vectors in non-linearly. All right, and maybe also x. And also hyperbolic equations where it's scalar. Okay, only for scalar. We cannot do nonlinear system. So here is a nonlinear convection where f depends on u. It's nonlinear convection, maybe plus a nonlinear system. So clearly OD is included here because capital F is 0 is nonlinear OD. So OD is included here. All right. And of course, there are many applications from Jacobi here. I just give a few. And the way to do it actually is it's a paper I wrote 20 years ago with Stan Osher, where we use the level set equation, level set method to solve this. These are quasi-linear PDEs, all right? So we solve them by level set method. So we define level set function in high dimension, and originally the solution is dependent on t and x. Now we have another independent variable p. So this phi equals 0 when p is the solution of your nonlinear PDE. All right. So here p and x has the same dimension. So for Ham-Jacobi, right? Because here u for Ham-Jacobi, u is just gradient vector. So u or p has the exact same dimension x, which means we double the dimension. We double the dimension of the problem. So this cone on this graph, the cone, high dimension cone is phi. If you find it's 0, that gives you u. So the 0 level curve of phi defines u. All right. And that is a matter of just a simple calculus to show that if S solved Ham-Jacobi equation, then this phi actually solved this linear PDE. It's actually a well-known Liouville equation. This is a really classical Liouville equation. Well, now this H depends on X and P. H does not depend on phi. So it's a really linear PDE. Okay. And of course, by now we know how to solve linear PDE. General linear PDE can be solved by quantum simulation, right? If you Schrodinger, for example. And this level set method also works for the scalar nonlinear hyperbolic equation, which is the one I gave in the previous slides, and also nonlinear ODE. Okay. But one point I have to emphasize, this nonlinear PDEs usually they have singularity, right? For conservation law, you have shock. For nonlinear hyperbolic, you have shock. Ham-Jacobi, you can have cusp, which corresponding to caustics, right? So caustics is something that associated with geometric optics. So you do get the singularities, and beyond singularities, usually we have to use so-called Viscotti solution, right? That's something that people know. But here, what we get by this method is not a Viscotti solution, it's something called a multivariate solution. So probably not everyone knows what the multivariate solution is. Here's some graph which shows you. And here, if you have, for example, Burke's equation, if you start with sinusoidal function for initial data, eventually you get this solution because the speed depends on the solution. So eventually you form the shock on the right-hand side, okay? You form a shock. But here, the multivariate solution, basically, this is just the last, it's just solution get overturned. You get this multivariate solution. Well, shock, you just cut this triple value. You have triple value, so you cut it by the straight line using the equal area rule, that gives you shock. But we do not get a shock here, we get this multivariate solution. Well, for Ham-Jacobi also, again, the multivariate solution, you will allow linear superposition. And actually, there are a lot of applications where shock, shock is not, Viscotti is not the right notion. For example, for geometric optics or seismic waves, for seismic waves, if you care about not just first arrival, which is Viscotti solution, if you care about the multiple arrivals, they are multivariate solutions. And if you talk about Samichal's limit of quantum mechanics, or high frequency limit of any linear waves, from elastic wave to magnetic waves, you get these multivariate solutions, all right? So there are a lot of physical applications where the multivariate solution is relevant. But of course, there are also many applications like gas dynamics where the Viscotti is relevant. But we do not know how to get a Viscotti. So it remains an open question. And then, of course, when you have quantum algorithm, you have to make sure that you get quantum advantage. So here we make comparisons. If you have quantum algorithm based on this our formulation, then you compare with cost of classical, Essentially here we have table where so classical cost over the quantum cost, C over Q, you get d to the power with this space dimension to power R1. You want R1 to be positive, then you have exponential speed up, okay, for quantum algorithm. And this epsilon is the accuracy, all right? So 1 over epsilon to the power R2, you want R2 to be positive, then you have an exponential, you have exponential speed advantage over the accuracy. What that means is that if you classically you use n grid points, then the quantum algorithm needs log n number of points. So now for Hamming-Jacobi, as you can see, the R1 and R2 can be positive as long as the dimension is high enough. For example, this B has to do with initial data, forget about it. If D is bigger than 4, for higher than 4 dimension, we get quantum advantage, exponential advantage over the dimension. But if D is bigger than 9, you get quantum advantage, exponential quantum advantage over the accuracy epsilon. Okay. So you can achieve quantum advantage for Hamming-Jacobi equations, for scalar hyperbolic equations. But for general ODEs, you see both R1, R2 are negative. For ODEs, actually, we do not have quantum advantage. For general PDE, you can first discretize space, then it becomes ODEs, all right? And because ODE has no advantage, of course, I mean, this PDE, so if you do solve this way, I mean, you don't have a quantum advantage. So these remain open questions. So I give us a few open questions. For nonlinear equation, actually, is largely open. Okay, what we can do is rather limited. So for general nonlinear PDEs, how we've got solutions and high dimensional dynamics, for example, molecular dynamics, right? You have to solve a very large scale ordinary differential equations. And then, of course, what we are very interesting is this experimental realization, because if you can realize this, one of these Hamiltonian, quantum experimentally, then we can design quantum chip to solve this specific type of PDEs. So that's something we will currently working very hard with the physical physicist. Let me see. Okay, yeah, maybe have some time, a little bit of time to talk about this third topic, which is time-dependent Hamiltonians. And very often you have to solve it's a dynamic system with time-dependent coefficients, so the Hamiltonian can depend on time. Okay, and here we start with the unitary, I mean, Hermitian matrix. Here H is Hermitian, but depend on time. And the difficult with solving this kind of system is that this Hamiltonian are non-commutative in time. So if t does not equal to t prime, this I mean T and ht prime are non-commutative. So the analytic solution to this kind of system, you do have this unitary operator u, which is e to the minus I. You integrate from beginning time to the stopping time, and you have integrate this h of tau over time. And you have to interpret, you need this t, the operator is the time ordering operator, all right? You have to order the time in the right way, because otherwise the solution is not right, because this h are non-commutative. So this usually one has to use so-called Dyson series to interpret this time ordering operator. So these are Dyson theorems, and you have an infinite series, and you have to truncate. Numerically, you have to truncate. All right, so you need to use Dyson series. It's very complicated, actually. So this is the state-of-art algorithm for using Dyson series. I mean, for example, this is an algorithm by Lin in Berkeley, where they have to evolve for the one-time step. Yeah, then you have to take a measurement. And as I mentioned before, the measurement, quantum measurement is very difficult to do. But you have to take, their algorithm have to take the measurement at every time step. So it's rather complicated. Okay. And also you have to do time discrete, because you have to interpret this by discrete time. Actually, what we did is we find a PDE in one dimension higher, which becomes autonomous. So this is the PDE we found, all right? So it's actually a linear transport PDE. In a one dimension higher, we have a new variable we call S, which plays the role of pseudo time. It's sort of time, okay? But it's not T, it's S. So you have linear convection operator on the right-hand side, but Hamiltonian now, before we had H of T, now it's H of S. So this is first is a linear PDE, okay? It's one dimension higher, right? We add one variable S. And this time is autonomous because H now does not depend on T. So how do you get back to original equation Y? So here we have this one multiplied, initial data will multiply by a function of S. And this S you can many choice. For example, if you choose S, G of S to be delta function of S, then Y is simply you integrate out S from W. You get the solution to original diagram system. You can, if you choose G of S to be 1, then Y is simply W by choosing S equals T. All right. So what do we do? And this works for both ODE and the PDEs. All right. So the H can be any linear operator. It can be differential operator. All right. So the story is that it goes to one dimension higher than PDE with a linear, we get a linear PDE with conversion term is so-called pseudo time variable. So what's good about this is if you start with linear ODE and PDE, I mean, this W equation is still linear. All right. Of course, I mean, a lot of people know, well, I know how to make a non-autonomous system autonomous. And people always do this, mathematicians. You just, okay, I introduce another variable tau, very similar to what we did. I call this T to be tau, then add another ODE, d tau dd to be 1. So I still get ODE, all right? That's what people do. But notice now, if tau is dependent variable, if original equation is linear, now you have a nonlinear equation. If you do this classical way, a linear ODE or linear diagram system become nonlinear. Now you have h of tau, y of t. That's a nonlinear operator. And as I said, the quantum computer does not like nonlinear equations. But look at our W equation. If the original system is linear, we remain linear. Okay, so this makes it easy for quantum computer. And so that's for unitary operator. For general non-autonomous ODE PD, of course, you can first do Schrodinger to make the Schrodinger operator. Then you change this non-autonomous Schrodinger into this autonomous Schrodinger by adding one more dimension. All right. And another thing compared with Dyson series that our formulation is time continuous and space continuous, which so our formulation works for both this analog quantum computer, continuous variable, and the qubits. Of course, you can discretize our system, then you can use qubits. So it works for both continuous variable and qubits. Well, the last part, I probably don't have time. Essentially, we also, if you have PDOD with usually coefficient can be uncertainty. I mean,
yeah,
come from experiment.
Just a comment. There is no time limit on the seminar. You can talk as much as you want.
Oh, okay. Maybe 5 minutes. Yeah, sure.
Yeah, okay. Yeah, take your time. There's no rush. Yeah.
Okay, sure. Yeah, so it's this journal work also with Francois Gauss. So actually, I mean, I learned this idea from him 10 years ago. So if you want to solve ODE with a random coefficient, very often, I mean, this ODE has coefficient which come from measurement, experiment. I mean, it's not first principle. PDEs are not first principle. You have this uncertainty. And usually uncertainty is modeled by some random variable Z, right, in very high dimension. So very often people do Monte Carlo simulation, right? If you have stochastic or random PD, you do Monte Carlo simulation. You take a lot of samples of Z, and you then take ensemble average. You solve this PDE ODE many times, all right? So it'll take a large number of samples. You solve this equation M times. M is usually very large because Monte Carlo has low convergence rate, right? The area is 1 over square root of M. So if you want L to be 10 to the minus 3, you have to solve this equation 1 million times, 10 to the 6. All right. And well, this is so this is actually a way, I mean, Francois, he showed me this trick. He was not one quantum computer, all right? He was using this method to solve homogenization problem because homogenization, I mean, this Z can be an oscillatory variable, all right? And you want to find the average of U over these fast variable oscillations. And there are a lot of theory like by Luc Tatar, Miller, and those compensated compactness, and so on. There are a lot of techniques. But he did, I like this idea. So he basically go to high dimension by introduce a new transform, new variable W. So he called this capital U, which depend on T and the random Z and W to be A of Z. Over here, I'll assume A is positive. A to Z, E to the minus W A of Z times U. W is positive. Then this capital U, actually, if little u solve this little ODE with a coefficient A of Z, capital U are actually solve this linear transport equation But now this linear transformation has no A of Z. So this random dependence of coefficient disappear. And of course, it appears only on the initial data. All right. Now to recover U, you just integrate over W. You can recover E capital U. And now, if I have a Monte Carlo for this PDE, and if I want to get ensemble average, I just have to take ensemble average of the initial data. Because now the PDE does not depend on no coefficient that depend on Z. I just solve this PDE once, starting with ensemble average on Z, and solve the PDE only once. I get ensemble average of solution of U, right? Because the linear PDE and the equation does not depend on Z. So which means I can do a Monte Carlo simulation by solving this PDE only once. Okay, the cost is independent of the number of samples. I don't know if you know, you can do Monte Carlo this way, I mean, for classical computer, but now going to high dimension, we can do that. And actually, you can do this for all kind of PDEs. For example, the heat equation, where when the heat conductivity is uncertain, same transformation, you get this third order PDE that we use for Schrodinger, right? You get rid of the A of Z. For linear transport equation, when the scattering coefficient, usually if you do wave propagation scattering coefficient, you never know what it is. People do experiment on it. So here, this is neutral transport, for example, sigma Z is the scattering coefficient, scattering rate, and same transformation, then the right-hand side, you get actual derivative in W, and you actually can prove that this is well posed. And now the PDE does not depend on no coefficient that depend on Z. So you can do the same idea. And for convection equation, and that same trick does not work actually. I mean, here is the first order derivative in X. You have this index of reflection can be, you have wave propagation through some media where the index of reflection may be uncertain. You never know what that is. Okay, depend on Z. If you same idea, same transformation actually does not work because now you get this mixed derivative here, dx dw, and this is bad equation. Actually, it's opposed. But what you can do is take a square root of A of Z. Then actually get third order PDE. You get two derivative in W. And now this is a good PDE. This third order PDE is very similar to this Schrodinger equation. So that's a good equation. And you can do it for Schrodinger equation when it was make difficult with Schrodinger equation is that the potential, you never know what the potential is. So you can assume the potential depends on some uncertainty variable A of Z. You do this square root transformation, then this A of Z disappear. You only have this V of X, right? Of course, you say, well, this is very special. I mean, this potential is a function of Z times function of X. That's very special. Now let's do a not very special one, all right? So now let's consider general case A, which well, it's not completely general, but it's a function of Z times function of X, but you need many terms. You need L terms to do this. Of course, this is not the most general function of AXZ, but that's essentially what people do in the community of uncertainty computation. For example, if for any stochastic field, if you do Calhoun-Loewe expansion, you find a orthogonal basis, okay, in Z, then the coefficient only depend on X. Or if you so-called stochastic looking, and if you know the distribution of Z, you just use orthogonal polynomial, use molecular calculus. Right, you find a orthogonal polynomial that depends on Z, okay, and then this stochastic Galerkin expansion, the coefficient does not depend on Z. So this is as general as people in uncertain computation do, okay. In this case, and then now this new variable W has to be L dimension. So you need a vector of dimension L to get rid of all this AI of Z. So you now the capital U is just the product of all this L dimensional product. Then you get this, start with this heat equation, for example. You end up this equation of capital U, where now the coefficient, of course, you have a new actual L dimensional derivative in W, but now the coefficient only depends on BI of X, no more Z. All right, so now I'm just summarize what we have done. Well, to just repeat, the quantum computers can only know how to solve a Schrodinger equation. All right, that's called quantum simulation. And for other PDEs and ODEs, even with boundary conditions or infinite conditions, so we found this simple transformation by going to one dimension higher and plus a Fourier transform, they become Schrodinger equation. So essentially we Schrodingerize everything, all right? So all the linear PDEs just going to one high dimension, it becomes Schrodinger equation. And well, this transformation seems too new. I mean, we have done this for over a year. I ask all the mathematics I know, have you seen this before? And so far, and nobody has seen this before. So it seems to be new, this idea. And also another advantage of this, our formulation is based on continuous variable. We do not have to discretize. So it allows us to do continuous variable formulation. Namely, we can do analog computing. Of course, I mean, you can also discretize and use digital computing. I mean, it can be done, and all hybridization of the both, right? For nonlinear PDEs, of course, what we can do is rather limited. It's largely open, all right? We can only do nonlinear Hammond-Jacobi equations and scalar conservation law. The idea is to use level set with double the dimension, go to higher dimension, then becomes linear, all right? And for non-autonomous system, again, we go to add one dimension higher, it becomes autonomous. And still linear problem remains linear by this idea. And if you have an uncertain problem with PDOD with uncertainty coefficients, if you want to do Monte Carlo simulation again, we go to high dimension, we make the coefficient, random coefficient disappear, all right? And then you only, to find ensemble average, you only have to solve this PDE once. So these are some philosophical thinking about this business. It's I mean, not everyone agree with me, but this is basically our philosophy. For the last 100 years, all right, all mathematicians and physics have been working very hard to reduce the dimension. The reason is that classical computer have this curse of dimensionality. So there are all these theory, mathematical ideas to reduce dimension. For example, you start with very high dimensional PDEs, for example, n-body Schrodinger equation, all right? You take dimension reductions, coarse graining, you take mean field limit, you take moment closure, and so on. The goal is to bring dimension down so classical computer can solve it. Of course, the price you pay is that you may start with a linear equation, you end up at nonlinear equation. You start with n-body Schrodinger, you end up at nonlinear Navier-Stokes equation, for example, all right? So these are problems that quantum computer cannot solve. What we have been doing, at least we have this systematic way of doing all these different problems. Is the opposite. Okay, what we do is we go to higher dimension, but not too high. We're not going back to n-body Schrodinger, right? We either go to one dimension higher or we double the dimension, all right? Because for quantum computer, you use qubits. You take a log, whatever cost, classical cost, take a log. So it's not afraid of dimension, as long as you do not go to too high dimension, all right? We double or add one dimension, that's nothing for quantum computer. So this is what our approach. We go to opposite direction, we lift to higher dimension, which make a nonlinear PD to be linear and linear PD to be Schrodinger equations. All right. Also, by going high dimension, we make non-autonomous system to be autonomous system. We make random PDs to be deterministic PDs, or by going to high dimension. So this, of course, needs new mathematical thinking. For the last centuries, all the mathematicians and physicists have worked hard to reduce dimension. So there are a lot of important tools developed. I think if you care about quantum computer, probably it's time for mathematical community to think how to go to the opposite, how to go to high dimension to make the problem solvable by quantum computer. All right, so that's our our philosophy. All right, take home message. I mean, it's busy time. People are going home now. If you get stuck in low dimension, the idea is to go to high dimension. Well, with that, I stop here and thank you very much.
Yeah, thank you very much. Thank you. Any questions? Yeah, Ting, do you want to unmute? Yeah, someone asked you on the chat.
I saw some questions. Let me see.
Yeah, Ting, do you want to unmute?
Well, Rick Gibson. Oh, he just signed. Okay. It's Nico Yuki. I apologize. Okay.
Very, very last one. Yeah.
The last one. Okay. May I ask whether your polynomials can be used to inverse? This is a very good question, and we have been thinking about it. The difficulty with inverse problem is that even the forward problem is linear, the inverse problem becomes nonlinear. So it needs some new ideas. I mean, it's something we are very interested, but so far we haven't had a clear idea how to do it. It's a very important problem. Definitely something that in our agenda, we hope we'll be able to do it one day, but not yet.
So continuing with these questions,
Hi, Eric.
Hello everyone. So if you continuing with this interesting question about inverse problems, so assume you take just the model that you discussed with Francois Gauls, right? So this here ODE, and assume you are trying to identify the coefficient A, right?
Yeah.
That would be somehow the simplest inverse problem.
That's true. That's true. Yes.
So maybe your idea of moving into a transport equation can help, right? Because then it's about like identifying the initial datum.
That's true. Yes. That's certainly true. Yes.
So maybe I think in inverse problems, maybe the difficulty comes because you need to do the extension, right? So and then I mean in the inverse problems, of course, you have partial measurements on the solution, right?
Yeah.
Maybe the question is how do you lift to this higher dimensional space the partial information you have on the solution in the original model out of measurements, right?
Yes.
Yeah.
That's right. I talked to Sid Mishra at the ETH a little bit about this. I mean, there are several ways. Why is the quantum computer, and also another way.
Can you go back?
Learning actually, and he tried it. I mean, so far the result is not very good, but I realize what the problem is. I was talking about it. I mean, so certainly this going to higher dimension might be interesting for both machine learning, classical computer, I mean, machine learning, or I mean, quantum computer. Certainly, it's a direction that's very fascinating to pursue. I mean, we haven't done much, but certainly something we are very interested in doing, and certainly would be happy to, I mean, work with you if you're interested in this direction.
Yeah, Giancarlo, do you want to ask your question live?
Hi. No, my question was, how about stochastic differential equations that are not of Black-Scholes type? Or my guess is that you're always transforming the problem that you have into a PDE, and then let's say massage the PDE in a way until you reach this Schrodinger equation.
That's right. Actually, we are finishing a paper on stochastic. We start with ODE. Linear ones, and yeah, I mean, this generalization idea certainly works. There are some tricks we played, I mean, to make it really work, because I mean, this, if you have a Brownian motion and things like that. But yeah, we are finishing a paper on this. We know how to do it.
I'm going to ask something that looks like a bit of a curveball. You've heard about this JKO type schemes that exist. How do I say it? So there's this technique called energy minimization to solve PDEs, and although it's very nice, very robust, not all necessary PDEs will be able to be written as an energy minimization as the solution to the minimization of a certain energy functional.
Yes.
Okay, but there is a bunch of tricks on which these could still be where you could write the equation as the solution to some other energy minimization plus some extra bits, and then you plug everything together. So my question is, do you think it would be feasible to say combine the quantum computing bit where you could use and leverage all the tricks that you've been showing us, and then combining with standard computing on the side that does the bit that wouldn't fit the quantum computing element? Does my question make sense?
I'm not sure if I completely understand. Something that's related to this is this direction called quantum machine learning.
Okay.
Where basically this VQE, variational quantum eigensolver. What people do is that essentially you have a quantum circuit with certain parameters. And then you put into classical machine learning by minimize some loss functions. You find you optimize. You find the good parameters, which is sort of optimize your quantum circuit. So that's sort of, I don't know if that's really sort of similar to what you do, because there you minimize the loss function in the classical machine learning. Where the sort of equation to solve is basically this quantum circuit. You want to design the best quantum circuit. So that's something quite popular now, which might be related to what you're talking about. I probably didn't get your message 100%.
No, it's okay. It's okay. I think you gave me an answer that goes into the right direction. Thank you.
All right, thank you. Other questions?
Yeah, may I?
Yeah, sure.
Sure.
The warped phase transformation, maybe you can go to that slide.
Which transformation for Schrodinger relation?
Warped phase
Sure.
transformation.
Yeah.
I was wondering, where is the phase in this expression?
So this one.
It's the very beginning of your talk.
That's where I first introduced this transformation is here, it is page.
Yeah, e to the minus p for every positive p.
Yes.
Is this what does the phase transformation?
Yes.
So
you just multiply the u by e to the minus p, then you get the equation for this w.
So is it just a name or it has some physics here?
Your connection is probably not well.
Do you hear me? Is it just a name,
from your
a label, or is there some physics meaning to this e to the minus p?
That's a good question. People always ask what is physics significance. Well, so far for me, it's just a mathematical bridge to transform a non-Schrodinger into Schrodinger. But it's a little bit like it's a little bit like a Laplace transform, but it's not exactly Laplace transform because this p is not t.
Yeah, the
idea is that people say why you must be very crazy to multiply something by e to the minus p. The idea is that you need this I, right? The difference between heat equation. You want how to get the I.
Yes.
Well, the physicists they get I by changing t to I times t. That does not work for, and I mean, then the solution agrees when t goes to infinity. Then you get the same solution, but evolution solution do not get. So here, basically, if you get to get I, e to the minus p, the derivative is basically itself. Once I have p derivative, take for a transform, we get I. So I mean that's. Well, it's not. That's not how I found it. We found this because I was doing this with Francois on the other problem, and then all of a sudden we realized the connection with Schrodinger. But if you think, I mean, from the beginning, why you need either minus p because you need the actual derivative. With derivative, we can do for a channel, we get I. So that's why it works this way. I don't know the physical significance of this W equation. I have no idea.
Okay, is there?
But the fact that every linear PDOD, if you go to one dimension higher, becomes Schrodinger. I mean, it must have some physical significance. I don't know. I mean, because it's very interesting. You just need to go to one dimension higher. Essentially, all PDEs are Schrodinger equations.
Yeah. Can I connect it to
I don't know if I heard of anything like this before. I have asked, everyone I met, have you seen this before? Nobody seems to know this.
Can I connect it to the optical lattice? Because you had, at some point, you said warped optical lattice.
Optical lattice?
Optical lattice. Warped optical lattice. And then some of your
geometric optics, you mean? You mean I mentioned?
Yeah, you mentioned it, and I tried to connect it, and also to think about space-time, warped space. You know, in Einstein's theory, we have warped space-time, where the space is warped, and that explains the whole story of black holes.
Yes.
So anyway.
Yeah, well, some physicists said, well, there's quantum field theory, which might be related. I mean, I have no knowledge about those areas. For me, it's just a mathematical way to get a Schrodinger equation in the simplest possible way. There might be some physical significance, I don't know. I mean, for analysts, I mean, some very good analysts are interested in this because they said they may provide some new way to understand the PDE. I mean, because essentially it's Schrodinger. Actually, Enrique, when he first saw this route, he mentioned this kinetic transformation, which he transform is transforming between the wave equation and the heat equation. It's different transformation. Only works for that setting, but our transformation seems to work for general differential equations. But certainly, I mean, for analysts, they are interested in looking at this PDE from a completely different angle, right? So some analysts is, interested in this because they think it might provide some new understanding of these classical PDEs. Yeah, I don't know physical interpretation of this new equations. I don't know.
Okay, I want to be more naive now.
Mm-hmm.
Can I use the homogenization technique?
Yes.
To smooth the warped space?
Yeah, in homogenization, very often you introduce a new variable. For the fast variable, it goes to high dimension. And also this idea by Francois goes, he was doing homogenization by introducing this actual variable. So certainly, yeah, we have a paper on multi-value multi-scale problem where we use this so-called iterative homogenization by adding actual variable for fast variable equal to high dimension. And then you can use this quantum algorithm. Yeah, we have a paper on that also for homogenization problem.
Okay, thank you.
Thank you.
All right. Yes. Yeah. Other questions or comments?
If I may.
Yeah, sure. Go ahead, please.
It's common in machine language or AI, machine learning, sorry, and AI and topological analysis. People go to the higher space, high dimension, and then project on the low dimension and get some information from that. I know that your talk is not geared in that direction at all, but maybe one can...
Yeah, sure. I mean, what we did is also we go high dimension, solve it, then we have to project back, right? I mean, yeah, to get back to the original equation, you have to take moments. You get back to the U by getting rid of the P. So yeah, I mean, well, in geometric optics, the work I did with Tong was to go to high dimension, you sort of unfold singularity. You have different understanding of the equation in that. And also in nonlinear PDE community, there's, for example, hyperbolic equations. This work by Lyon's Paton-Tenemo, where they also use kinetic formulation. Also, again, by going to phase space. And then they also numeric method, so-called kinetic scheme. By going to phase space, you get nonlinear convection, which easy, I mean, make the visualization easier. So there are all these ideas by going to high dimension for different purpose. Right. I mean, so going to high dimension, I mean, we're not the first one to go to high dimension. People have done that. But for this setting, for this systematic way to solve PDE problem for quantum computer, I mean, this Schrodinger idea, at this point, nobody told us they have seen this before. So.
Okay, wonderful. Thank you.
Yeah, for the matrix, for them, people do this quantum dilation. I mean, this Stein spring method. There are this quantum dilation method. If you have expanded general matrix, expand the matrix to become a unit matrix. I mean, that's called quantum dilation. People use two-block encoding. They do that. And what the difference with us? First, we have systematic way of do general PDEs. Number two, we are based on continuous variable, so it allows implementation of our algorithm both continuous variable version or qubits. So this certainly is more general and works for all scenario.
Okay.
All right. Yeah. Thank you, Shi Jin, for the nice talk. And
sure. Thank you very much for
much.
arranging this.
Yeah. Thank you. So yeah, we'll continue our discussions later on with the other group. Yeah.
Okay.
Yeah.
Thank
you.
you. Thank everyone for coming to my
Bye.
talk.
Bye.
Bye bye.
Thanks. Bye.